Welcome students to the lecture in some examples of modern communication system. Now, in this lecture we will consider some aspects of mobile communication as well as satellite communication. So, let us start with the basic link analysis of a satellite communication. As you can see in the picture, the basic satellite link is given. In this, from the transmitting end, we have a high power amplifier on our station, which is transmitting to the satellite. At the satellite, we have receiver down converter, then TWTA, traveling wave tube amplifier. The satellite retransmits the signal to another earth station. The signal is received by a low noise amplifier. The link is clearly visible in the figure, as you can see, and all the quantities, that is the gain of the antenna receiving as well as transmitting, the EIRP transmitting of the earth station, the EIRP-S, that is EIRP of satellite. So, referring to this figure, we will look into some details of a link analysis. So, the transmit earth station transmits the carrier ST, whose power is the EIRP of carrier, given by EIRP is PT into GT. PT is the carrier power at the antenna feed and GT is the transmit antenna gain. Assuming the clear sky conditions, the only attenuation carrier ST suffers is the uplink free space loss. The atmospheric attenuation and the antenna tracking loss. The uplink free space loss is given by, as you can see in the expression, LU is equal to 4 pi du by lambda u the whole square, which can be written as 4 pi fu du by c the whole square, where du is the uplink slant range in meters, lambda u is uplink wavelength in meters, fu is uplink carrier frequency in hertz, and c as usual is the speed of light, that is 3 into 10 raised to 8 meters per second. SUT is the carrier received at the satellite in the uplink. U stands for uplink. NUT is AWGN, additive wide Gaussian noise with 0 mean, which adds to the uplink carrier. L is the sum of antenna tracking loss and the atmospheric attenuation. GU is the satellite antenna gain. CU is the uplink carrier power, the power of SUT. So, CU is, as you can see, is given by ERP multiplied by GU divided by LU and L, which can also be written as again EIRP by L into C by 4 pi FU du the whole square multiplied by GU. Now, NU is the uplink noise power, where NU is given by KTU into B. TU is the satellite system noise temperature in Kelvin and B is the noise bandwidth of the satellite channel. So, it gives you the uplink noise power. Now, the parameter GU by TU is the satellite antenna gain to noise temperature. C by NU is the uplink carrier to noise ratio, which is given by, as we can substitute for CU and NU and we can find this uplink carrier to noise ratio, and it is given by EIRP LU by L GU by TU into 1 by KB. Now, SUT plus NUT is the received carrier plus noise at the satellite. This carrier plus noise is amplified and down converted by the receiver down converter and then amplified again by TWTA, traveling wave tube amplifier, and retransmitted back to the earth station by the satellite antenna. SU, S cap and N cap, see the notations here, are the retransmitted carrier plus noise, which has the same carrier to noise ratio as the received carrier plus noise. Therefore, C capital cap U by n capital cap U is equal to C by n of U. Now, let ERPS, it is also shown in the figure, be the satellite ERP, then Cu cap, the retransmitted carrier power, Cu cap is equal to ERPS. Nu cap is the power of accompanied uplink noise NUT. Nu cap is EIRPS divided by carrier to noise ratio of uplink, that is C by NU. Now, S cap plus N cap plus ND is the received carrier plus noise at the receive earth station. S cap plus N cap are the attenuated version of S cap U plus N cap U, and NDT is the additional independent downlink AWGN with 0 mean that adds on to S cap T. Therefore, the carrier power at the receive earth station C is given by ERPS G divided by LD into L1. Now, what is this L1? L1 is the sum of antenna tracking loss and the atmospheric attenuation on the downlink. DD is again the downlink slant range, FD is downlink carrier frequency in hertz. The power of the accompanied uplink noise appearing on the downlink, as you can see here, is given N cap is given by N cap, which is equal to N cap U G divided by LD and L1. So, when you substitute the values, we get the final expression for N cap as it is shown here. The downlink noise power again is given by ND is K T into B. T is earth station system noise temperature. Thus, the composite noise power at the receive earth station, that is N is equal to capital N cap plus capital N of D, is given by the expression which can be obtained by substituting the values of capital N cap plus capital N D. Therefore, the carrier to noise ratio of the overall satellite link is C by N, which is equal to, you can substitute the values and you can get the expression as it is given in the picture, and you can see the expression in the picture, the carrier to noise ratio of the overall satellite link. This can be expressed just by few mathematical manipulation. We can express the overall overall carrier to noise ratio of the link by the expression C by N is equal to the whole inverse of C by N U inverse plus C by N D inverse. Now, this is an important expression which we have derived, and where this C by N D, that is C by N U, has already been defined. This C by N D is actually the downlink carrier to noise ratio, which we are adding here in this expression. Now, link EB by N naught. EB is the transmitted energy per bit. If all the carrier waveforms have identical energy EB during any signaling interval, then C is equal to EB by TB and N is equal to N naught B, because it is affected by AWGN. N naught by 2 is the double sided power spectral density of additive white Gaussian noise. Therefore, EB by N naught can be written as TB into B to C by N. C by N is the overall carrier to noise ratio of the satellite link. So, let us look at an illustration of how this link can be calculated. So, for illustration I have taken one example. Consider a KU band, that is 1412 gigahertz band satellite system operating in the single carrier per transponder TDMA mode, TDMA time division multiple access, and using QPSK carrier modulation. The system parameters, as you can see, are as follows. First of all, the carrier modulation parameters, the bit rate is 60 megabits per second, bit duration bandwidth product is 0.6 and noise bandwidth is 36 megahertz. These are the satellite parameters. Antenna gain to noise temperature ratio 1.6 dB per Kelvin, and satellite saturation EIRP is 44 dB watts. The earth station parameters, antenna diameter is 7 meter, transmit antenna gain at 14 gigahertz is 57.6 dB, receive antenna gain at 12 gigahertz is 56.3 dB. Carrier power into antenna is 174 watts. Slant range uplink as well as downlink is 37,506 kilometers. Tracking loss is 1.2 dB uplink and 0.9 dB downlink. The system noise temperature is equal to 160 Kelvin. So, we can calculate the calculations are shown here for the uplink 14.25 gigahertz. The carrier EIRP comes out to be 80 dB watts, free space loss is 206.9 dB, antenna tracking loss is 1.2 dB, satellite G by T gain to noise temperature ratio is 1.6 dB per Kelvin. Boltzmann constant you know already. Noise bandwidth has been calculated like this, 10 log 10 of 36 megahertz, that is 36 into 10 raised to 6, which comes out to be 75.6 dB hertz. And the uplink carrier to noise ratio, as you can see, is calculated and is found to be 26.5 dB. These are the calculations for downlink at 11.95 gigahertz. Again, satellite EIRP is found to be 44 dB watts, free space loss is 205.5 dB, antenna tracking loss is 0.9 dB, earth station G by T which has been calculated to be 34.3 dB per Kelvin. Boltzmann constant is 228.6 dB watts per Kelvin hertz, and noise bandwidth is 75.6 dB hertz. See each and everything we have calculated in decibels, so that overall carrier to noise ratio simply by adding all these calculations. So, the carrier to noise ratio for the downlink is found to be 24.9 dB. The carrier to noise ratio of the overall satellite link, again using the same using the formula which we have derived, 10 log 10 of Cn is 10 log 10 of C by n U inverse, C by n D inverse, the whole inverse, and it is found to be 22.6 dB. The link EB by N naught, as we have already studied in the previous lectures, EB by N naught is actually analogous to the signal to noise ratio. So, the link EB by N naught is found to be 20.4 dB. So, this is how we can carry out the basic link analysis and find the overall carrier to noise ratio of a satellite link. Now, let us consider some more details of mobile communication. So, we will start with a very important aspect, that is handoff strategies. The handoff operation not only involves identifying a new base station, but also requires that the voice and control signals be allocated to channels associated with the new base station. Processing handoffs is an important task in any cellular radio system. Many handoff strategies prioritize handoff requests over call initiation requests when allocating unused channel in a cell site. Handoffs must be performed successfully and as infrequently as possible and be imperceptible to the users. In order to meet these requirements, system designers must specify an optimum signal level at which to initiate a handoff. See, there is a little bit gap between initiation of a handoff and completion of an handoff. So, first the handoff is initiated and then it is completed in some time interval. So, we will see once a particular signal level is specified as a minimum usable signal for acceptable voice quality at the base station receiver, a slightly stronger signal level is used as a threshold at which handoff is made. This margin, as you can see, is given by denoted by delta. Delta is these are actually the thresholds, the PR handoff at which the handoff takes place minus PR minimum usable. This margin cannot be too large or too small. If delta is too large, unnecessary handoffs will burden the MSC, mobile switching center, may occur, and if delta is too small, there may be insufficient time to complete a handoff before a call is lost due to weak signal condition. Therefore, delta is chosen carefully to meet these conflicting requirements. In the figure, we have illustrated the handoff situation. We will look at the figure just now. This figure demonstrates the case where a handoff is not made and the signal drops below the minimum acceptable level to keep the channel active. This dropped call event can happen when there is an excessive delay by MSC in assigning a handoff, or when the threshold delta is set too small for the handoff time in the system. Excessive delays may occur during high traffic conditions, due to computational loading at the MSC, or due to the fact that no channels are available in any of the nearby base station, thus forcing the MSC to wait until channel in the nearby cell becomes free. So, in deciding when to hand off, it is important to ensure that the drop in the measured signal level is not due to the momentary fading, and that the mobile is actually moving away from the serving base station. In order to ensure this, the base station monitors the signal level for a certain period of time before a handoff is initiated. This running average measurement of a signal strength should be optimized so that unnecessary handoffs are avoided, while ensuring the necessary handoffs are completed before a call is terminated due to poor signal level. The length of time needed to decide if a handoff is necessary depends on the speed at which vehicle is moving. As you can see in the picture, it shows you the two situations of the above situation is that when handoff is initiated, but it is not completed and the call is dropped due to poor signal condition, whereas the second is the successful handoff, and you can see the figure. Now, let us come to the interference and the system capacity. See, both are the system capacity of course is dependent on the interference. So, interference is the major limiting factor in the performance of cellular radio systems. Source of interference include another mobile in the same cell, a call in progress in a neighboring cell, other base station operating in the same frequency band, or any non-cellular system which inadvertently leaks energy into the cellular frequency band. Interference on voice channel causes crosstalk, where the subscriber hears interference in the background due to an undesired transmission. So, on the control channel, interference lead to missed or blocked calls. These are the ill effects of this. Due to errors in digital signaling, interference is more severe in urban areas due to greater RF noise floor and large number of base stations and mobiles. Interference has been recognized as a major bottleneck in increasing capacity and is often responsible for dropped calls. The two major type of system generated cellular interference are co-channel interference and adjacent channel interference. Now, first let us consider the co-channel interference. Co-channel interference means interference between the cells which are using the same frequency bands. Frequency reuse implies that in a given coverage areas there are several cells that use the same set of frequencies, as I have mentioned, co-channel cell. These cells are called co-channel cells, and the interference between signals from these cells is called co-channel interference. Unlike thermal noise, which can be overcome by increasing signal to noise ratio, co-channel interference cannot be combated by simply increasing the carrier power. This is because increase in the transmit power increases the interference to the neighboring co-channel cells. To reduce co-channel interference, co-channel cells must be physically separated by a minimum distance to provide sufficient isolation due to propagation. So, the size of cell is approximately the same. We try to keep it nearly the same. The base station transmits the same power. The co-channel interference ratio is independent of the transmitted power and becomes a function of radius of the cell, which we will denote by capital R, and the difference between the centers of the nearest co-channel cells, which will be denoted by capital D. So, by increasing the ratio D by R, see the ratio, it depends on the ratio D by R, the spatial separation between the co-channel cells relative to the coverage difference of a cell is increased. Thus, interference is reduced from improved isolation of RF energy from co-channel cells. The parameter Q, called co-channel reuse ratio, is related to the cluster size. So, for you can see the relation here. For the hexagonal geometry, Q is D by R, which is under root 3 by n is the cluster size. So, a small value of Q provides larger capacity, since the cluster size n is small, whereas a large value of Q improves the transmission quality due to a smaller level of co-channel interference. So, a trade-off must be made between these two objectives in actual cellular design. So, co-channel reuse ratio for some values of n, you can see in the table, the cluster size when n is 3, the reuse ratio is 3, n is 7, 4.58, when n is 12, it is 6, and when n is 13, it is 6.24. So, these are some values of co-channel reuse ratio. Let I naught be the number of co-channel interfering cells, then the signal to interference ratio, that is S by R, which we also called as sometimes denoted as SIR, for a mobile receiver which monitors a forward channel, can be expressed as S by I is S divided by summation of all the I's. See, summation is carried over all the cells, all the interfering cells. That is why I subscript I is there, where S is the desired signal power from the desired base station, and I sub I is the interference power caused by ith interfering co-channel cell base station. So, considering only the first layer of see, there may be many layers depending upon the area, but we are considering only the first layer which interferes with the desired cell. So, considering only the first layer of interfering cells, if all the interfering base stations are equidistant from the desired base station, and if this distance is equal to distance d, capital D, between the cell centers, then the above equation can be simplified, and it is shown here. It is simplified to root 3 n to the power n divided by I naught, where n is the path loss exponent, its value may vary between 2 and 4. So, let us consider with this theory in background, let us consider this one example. So, this is the example. If a signal to interference ratio of 15 dB is required for satisfactory channel performance of a cellular system, we have to find the frequency reuse factor cluster size that should be used for maximum capacity. See, the requirement is 15 dB, right, for the satisfactory performance, and there are two cases where n is equal to 4. This is the path loss exponent 4 and 3, and in this it has been assumed that there are 6 co-channel cells in the first layer, all of them are at the same distance from the mobile. So, the first case n is equal to 4, let us consider 7 cell reuse pattern. The co-channel reuse ratio D by R is 4.583. The signal to noise interference ratio is given by S by I, which is 18.56. Since this is greater than the minimum required S by I, n equal to 7 can be used. We can use this cluster size. Let us take a look at n equal to 3. So, first let us consider a 7 cell reuse pattern. The signal to noise ratio, which is given by 12.5, since this is less than minimum required S by I, we need to use larger n, right. So, when n is 3, we cannot use a cluster size of 7. The next possible value of n after 7 is 12. The corresponding co-channel ratio for 12 is 6. The signal to interference ratio in this case is given as 15.56. So, when n is equal to 3, there is since this is greater than minimum required S by n, S12 can be used. So, for when n was 4, we can use the cluster size which is 7, but when n is 3, that is not sufficient, you have to use a cluster size of 12. In this lecture, we have discussed about the basic link analysis for satellite communication, and we have taken one example of the co-channel interference in mobile communication, plus some handoff strategies which are adopted in mobile communication. Hope you all might have enjoyed the lecture. Thank you.